Trophies?
What is that?
You know about trophies?
Trophies pizza. It's pretty good. I like their pizza.
It's by the McDonald's on the west loop.
They used to do a San Angelo to go card. They used to have buy one topping large, get one free.
Pizzas are cheap for the price.
Hold on.
So
They're
it's
free
San
large?
Angelo, San Angelo to go cards. Yeah, it's buy a one topping large pizza, get a one topping large free. And we would typically add 2 or 3 more toppings that maybe adding like $2 to it.
That place is good, but it's kind of ghetto.
Hey, that's some of the best food.
Yeah, you know what I'm saying?
No.
You know what I'm talking about?
No, but I did.
You walk in, it's like a little futon right here, and like half the employees are watching TV on the futon while the others.
If it's a slow day.
What?
If it's a slow day.
Yeah, it's a slow day.
All right, let's get through. So the exam key has been posted.
Oh no.
The rest of the exams, it's about halfway through. Though the rest of them will be finished tomorrow. At which time the grades will be released, so you can check it. Definitely, when you find a simplest model, all of those terms in the simplest model must be included in any post hoc test. That is 100% key. If you have an interaction, you take your subsets. Most people were good on that. If you don't have a significant interaction, there's no reason to do a subsets. Just run it. And the last question, our assumptions were met. Right? All assumptions are met, but we had a very large data set. So you can use your AIC, stepwise AIC, to find the simplest model. Your post hoc test then can default back to using ANOVA tables and tuples. No problem with that. All right? But if you tried to do classical tests to find the simplest model, it would have been very, very tedious. Use GL multi, get your simplest model, and then run your subsets on, use your subsets to investigate the interaction terms. So those will get released tomorrow. We left off here with the figure. I went ahead and uploaded an R script. It shows how you can remake it. Basically, I used if-else command that goes row by row. If it's a female, it adds in a new vector, it uses black. If it's a male, it's red. And then I pass that vector to the plot function. And I do that for pattern, and I do that for sex. All right, so sex was the colors, pattern was symbols, and I think based on what I could tell, I guess this was off. You can tell these circles, the open and the closed circles are slightly different sizes. The ones that I did in script, they look to be the same size. So that was 19 and 21, but you can see how you can do it. So the same thing would apply if you have, let's say, 3. Instead of doing if else, you would have to do some other type of if function. So you check for the first value, then you check for the second value, and then if that fails, do add that third value. In R, it's a little bit harder to do in R than it is in Excel. So Excel is actually pretty easy to do those types of statements. So if you were trying to make a figure like this and you needed, let's say, 3 or 4 different colors, 3 or 4 different symbols, you could probably get the symbol numbers and the colors set up in Excel and then get it transferred over to R. But that's been posted, so you can check it out. Also, I noticed I didn't have the key to exam 1 posted. That is posted, so you can see it. Definitely on these keys, I make some figures, but I don't do the full write-up. I don't do the full write-up, but I do go through and add commentary on the proper way to do the analyses, just like I've done with all. So that's up. So let's continue. So we introduced this idea that we have a continuous variable as an independent variable, all right? And we want to start to add even more complexity by not just restricting it to 1 continuous variable, but now introduce 2 and 3 and 4. All All right, so when we have this continuous variable, it really comes down to, are we using it as a covariate, or are we really interested in determining if it's a significant predictor? All right, the difference really comes down to how we're going to interpret it. So if it's a predictor variable, then we're saying that that value predicts some level of our dependent variable. So the size, the length of the fish is going to predict what our parasite load is going to be. If we're only using it as a covariate, we don't care what the relationship is. We're just saying, hey, they're correlated. Let's remove that effect and then investigate everything else. So, can a covariate be analyzed as a predictor variable? Yes. Is that how I typically do my analyses? Yes. All right. I don't mess with the ANCOVA because I do want to know, is this covariate actually a predictor? Could we use it to make a prediction about our dependent variable? All right. So this just kind of sets up the distinction between the two. And especially how you might interpret it. And then again, it kind of comes down to semantics. That's what it's about, not necessarily how we analyze our data. All right, so the predictor variables, yeah, we're looking at describing that relationship to the dependent variable, whereas the covariate, we're not really interested in that. We just want to remove the effect of the correlation and then include it. So yeah, with the covariate, if it's a non-significant term, we still leave it in. If it's being analyzed as a predictor, if it's non-significant, we just drop it. All right, so this leads to our assumptions. So with an ANCOVA, one of our assumptions is that the interaction term between our continuous variables and any of the other variables are not significant. All right, so that our slopes, that relationship between our dependent variable and that covariate is the same across all levels. With the predictors, we don't care if it's a significant interaction. That's just one of those things that we can test, or that we should be testing for. But we do have some assumptions that we need to confirm. So first three assumptions are assumptions that we've noticed, or that we've always been dealing with. The data are random and independent. They're normally distributed within each combination of groups, and the data are homoscedastic. All right, now you might be thinking, well, how do we get this normal distribution and homoscedasticity between all levels when we have a continuous variable, right? It's kind of hard to do that. So what we have to also look at then is the linear relationship. What we're looking at is, do we have the straight line relationship, or do we have something that is humped? So if our covariate, or if our continuous predictor increases, we want our dependent variable to also increase or to decrease. We don't want it to increase and then decrease. All right, we'll violate our linearity, and then we have to really adjust what our equations are going to be and how we analyze it. This last part refers to correlation among all the other variables. So with a single independent continuous variable, this orthogonality is met. All right, usually it's met, I should say that. Once we start having two and more continuous variables, then we have to pay attention to or have to consider the possibility that our independent variables are actually correlated to each other. All right? This whole term, variables are orthogonal, basically means that multicollinearity does not exist. All fancy terms are saying that our continuous variables are not correlated. How do we test it? Well, assumptions 2 to 4 are tested with GVLMA. That's that whole link function. That's our whole link function. We could do GVLMA. We could even look at our plot of the residuals to assess these. But the GVLMA and our residual plots tell us nothing about this orthogonality. In order to check that, we're going to look at something called variance inflation factors. All right, this function, VIF, is built into the CAR package. Very easy to do, but there are some rules on which values that are reported by the VIF function we'll use to determine whether or not this assumption is met. All right, and again, this assumption 5 only pertains to our continuous variables. All right, so multicollinearity. It's defined as correlation between our independent variables. All right. One predictor could be linear, or could linearly predict another variable, and thus we start to violate our orthogonality assumption. All right, so example here. We're looking at worm burden. All right, we have water temperature, season, and whether or not it's sunny or cloudy when we're out collecting. All right, water temperature could be predicted by the season. So what season of the year we are in, tells us, at least gives us an average of what our water temperature would be. Now, this inherently violates our independence. These two things are correlated. If we include them in there, we could see some rather interesting effects. All right. So in some cases, we may have one of those terms significant and the other is not. If we switch the order, if we drop one of the terms, all of a sudden that non-significant term may become not significant, or the significant term could become not significant, or vice versa. All right. So you can kind of flip depending on whether or not, as you're simplifying models, if you drop a term, all of a sudden this not significant term is significant, or vice versa. You can see it in some of the ANOVA table. Oh, that's kind of what that is, with the ANOVA tables. But also, if we look at the summary function. So when we create our summary, when we create our models, we're going to start to look at the summary. And at the bottom of the table, one of the stats that it reports is an F statistic and a p-value that is testing if our model does better than the null model. So if that model, with all of our terms that we have, that we've included, is that better than our null model? If we violate this multicollinearity assumption, we could have a situation where we have a significant F. So the model is better than the null model. However, none of the individual variables are significant, which then you're kind of at a loss, because we're saying, well, we need to drop our models. We need to drop terms, all the ones that are not significant, yet that term, that model is better than the null model. Kind of presents a paradox for us. Or we can see the reverse case, where we have significant terms in the model, but when we compare our model to a null model, so the one that has no terms, there's no difference in it. All right? Just in theory, if our model that we've created is no different than the null model, then you always go for the null model. But with all of our ANOVA simplification stuff, we've said if those terms are significant, we need to leave them in. So you can see how we can start getting some really funny results that'll leave us in a quandary on how to analyze our data. So the best way to go about doing it is to check our variance inflation factors first before proceeding with our model simplification. All right? And then proceed with your model simplification and recheck them. Recheck your variance inflation factors. All right? See, that's kind of what we said. If you're having difficulty choosing, check your variance inflation factors first. So what is this variance inflation factor? This is a proportion of variance in one predictor variable that is explained by all of the other predictor variables. All right, so it's kind of like a correlation. All right, if our variance inflation factor is equal to 1, then none of the other predictors in our model are explaining the variance in our variable of interest. As some of our predictor models start to explain the variance or the variation, our variance inflation factor will start to rise. Now, by their nature, categorical variables are uncorrelated. All right, red shirts, blue shirts, and then shirt sizes, they're independent. They are orthogonal. So this is really only applying to our continuous variables. We calculate this variance inflation factor by performing a regression analysis of our target variable against all of the other variables that are included in our model, all of the other predictor variables in our model. And then our variance inflation factor would be this 1 divided by 1 minus r squared. And I can't remember if I pointed that out or not, but we're not so much interested in it because R will generate the VIFs for us. All right. Now our interpretation, our guidelines, is if we have a variance inflation factor greater than 5, then we may have some problems with this multicollinearity. If we have a variance inflation factor larger than 10, we definitely have problems. All right, so 5 is kind of like the caution point where we probably need to start doing some stuff. At 10, it's without a doubt, we need to. All right, so what do we do if we see variance inflation factors that are greater than 5? We'll say greater than 5. Well, what we can do is remove the terms with the highest variance inflation factors and then recheck our model and the VIFs. And hopefully, we're removing the least biologically meaningful one first if we have high ones. So this isn't going to be we start with the highest VIF first and work backwards. No, you look at all the VIFs that are greater than 5 and say which one is the least biologically significant. All right, so if we had season and water temperature, actually change it to season, we'll say day of the year. All right, so it's a continuous number. All right, which one's probably the least biologically significant? Probably day of the year. Let's include water temperature, drop day of the year. Even though the water temperature might have a higher VIF. All right, so target the ones that are least biologically meaningful first, and then remake your model, check the variance inflation factors, and see if you've solved the problem. All right, you're going to keep doing this until all of our VIFs are below some arbitrary cutoff, and the cutoffs that we're going to use is usually 5. All right, so you keep dropping terms until we get to a situation where all of our VIFs are below 5. But don't do this arbitrarily. All right, think about what terms are getting removed and whether or not they have a biological meaning, or they can be interpreted biologically. All right, so how do we do it? Well, VIF, it's in the car package. So car is going to already be loaded normally. All right, but we're going to, and there are other VIF functions in various packages, but we're going to use the one in the car package. All right, we can generate VIRs for linear models. We can do it with generalized linear models. We can do it with linear mixed effects or generalized linear mixed effects models. All right, so VIF is going to apply for various types of models. Now, when we run this on models, we're going to get some different output. We're going to get a table of outputs. And I just kind of want to go through what's getting reported. All right, so when all of our degrees of freedom are 1, right, then we'll see a column called VIF. Right, and this is the column that we're going to utilize. And again, if we have a VIF greater than 5, we're going to probably have problems. We should start trying to fix it. As soon as one of our variables start to have more than 1 degrees of freedom, then we're going to start seeing a column called GVIF. GVIF, degree of freedom won't be there, and GVIF raised to the 1 over 2 times the n. All right, so what are these? GVIF is a generalized variance inflation factor. All right, you're going to have degrees of freedom for the variable, and then this other one is the adjusted generalized variance inflation factor. Anytime we have our columns appearing with this column, this is going to be the one that we use. What we're basically doing is adjusting the variance inflation factor for the degrees of freedom that we have. So if we had 2 or 3 or 4, we need to adjust that variance inflation factor to account for that. But our rule of thumb will still say the same. All right? We're going to look for a value of 5, but it's not going to be this raw value. Instead, we're going to actually have to square that value first and then compare it, which sounds harder than it is. because we can take VIF of our model and do this squared term on this one, and it'll automatically calculate the square of the values. So we're going to do this. So our example is going to use a data file or a data set that's in the car package. All right, so it's called Duncan. All right, so have your R open up, your R markdown, have car loaded. Duncan should be accessible. And let's take a look at it. So first question is, what is this Duncan data set? Did you look it up? Did you look at the help file for this by chance? So it's looking at prestige of an occupation. All right, so they basically go ask people, what's your view of, I don't know, an exterminator? Right, what's that? So yeah, they ask them, and they kind of looked at, the type of occupation that you're dealing with, the income of that occupation, the education, associated with that occupation, and then just perceived prestige. So you've got quite a few things. All right. So what I want you to do is just go ahead and make these two models. We're going to work with them. So mod 1 is just prestige as a function of income plus education, and then prestige as a function of income, education, and type. And we're going to use these to kind of look at some of the VIF tables and investigate the collinearity. I did call them mod 1 and mod 2. Did you make it? All right, so here's our summary. We've got two models. The difference between those two is the presence of the variable type. Presence of the variable type. And we're looking at the summary. So a couple things to notice. One, both models have a pretty high adjusted R-square value. So the models account for prestige. So knowing the income and the education level required for that job is correlated with prestige. It explains a lot of variation. Our F statistic and the p-value, yeah, that's better than the null model. All right, so it's important. When we include type, we explain a little bit more variation. Our adjusted R squared is 0.9, right? Still significant. But notice these two things that I have in red. So education, these aren't factor levels. All right? Income and education are continuous variables, so they're reported as numeric variables. So with income, all right, whatever unit income is, for every 1 unit increase in income, prestige is increasing almost by 0.6, whatever that value is. For education, every, let's say, 1 year increase in school results in an increase in prestige of 0.54. That's our interpretation, and both of these are significant. They're significant predictors. Once we include type, look what happened to education. Now that relationship with education dropped. Our income stayed the same, pretty close. Right? 0.5987 versus 5975. They're real close to each other. But for education, we went from 0.545, 0.546 down to 0.345. That's a pretty large drop in our relationship. So when we account for type, whether it's a professional type, white collar, or a blue collar type of job, education is less significant. All right. So what's going on here? Well, if we assume all of our assumptions are met, all of those first four assumptions, the last one that we need to check is variance inflation. Is there a relationship between income, education, and type that we're maybe missing? All right. So here's how we do the variance inflation. VIF, it's built into the car package. All we have to do is do VIF of our model. Right, so we've got our two models. And the very first one, it reports this. This is what it would look like if all of our variables have 1 degree of freedom. This is our variance inflation factors. Our rule, if any of these are greater than 5, you probably have a problem. But here, everything's less than 2. Everything's less than 5. So is there a correlation between income and education? I should say, is there a correlation that might be affecting our analysis? Probably not. Probably not. So let's look at mod 2. Now you can see we have a couple different things that get reported. We've got that generalized variance inflation factor. It's getting reported because we have one variable that has more than 1 degree of freedom. All right? It's because it has factors in that model. All right. So the column that we're interested in is this one, but we're not looking at the raw numbers. Rather, we want the square of that number. So what we can do is do the VIF of our mod 2 and square it to get this column. And this is the column that we're interested in. Because now we're dealing with numbers that allows us to use that 5, that cutoff value. I'm going to stress it's an arbitrary cutoff value of 5. So here, education appears to have excess variance inflation. All right, so our type seems to be correlated with education. Once we added it, we had a jump up. So you can see income 2.1 versus 2.2, education 2.1 up to 5.3. Once we included that second variable, we had a pretty large jump. So the question then becomes, how do we fix it? How do we fix it? Well, we fix it by removing a term. The question then becomes, well, what term is the least meaningful to this analysis? Is it going to be education, how much education you have? Or is it going to be the type, whether it's blue collar, white collar, or professional? What do you think?
Type.
Why type?
Well, I mean, everybody's parents said to them, go to college or you'll be a garbage man or something similar. So I would say that a blue collar job doesn't get as much prestige, and none of that had anything to do with the degree of education.
Okay, exactly. So just because we have a white collar, blue collar professional job doesn't necessarily mean that it required some education. Some jobs did. Some jobs did need a certain level of education, but not always. So perhaps our best approach then is to just go ahead and drop type from our analysis. When we do that, it gets back to a suitable type of analysis, suitable type of comparison. All right. So that's one way to do it. Another way we can look at our analysis is to look at those R-square values. All right. And I didn't make model 3. Model 3 has income and type associated with it. All right. So if we look at the R-square, adjusted R-squares, model 1 had 0.82, model 2 had 0.9. If we dropped education and kept type in there, we do explain more of the variance in prestige than if we include education and drop type. All right, I'll note that including both explains even more, but perhaps if you're undecided and say, well, I don't know which one is more biologically meaningful, take a look at the R's. Make this different sets of models and look at the R's and maybe go with the one that has the highest R squared. Here, probably not. I think I'm leaning towards keeping education because sometimes the type of job doesn't necessarily require a certain level of education, or may require certain levels of educations. Right, and we already talked about biological explanations, and I put this in quotes. Again, as you do these analyses, as you do your own analyses, try to avoid variables that replicate other variables or has the same amount of information. All right. So if you have, I don't know, cover, over a den site, it doesn't make, you have a percent cover, as a variable, and then maybe you have number of trees above 10 feet. Why include both? You already have a percent cover. I bet if you included them both in there, you're going to see some variance inflation problems. All right, so here's a full analysis. pmin.csv. All right, so it's posted. You can download it. I believe it's posted. I think I did that last week.
I don't think.
Just flight?
Yeah.
Yeah.
I didn't add it on here. I looked at it this afternoon. Oh, it's already on there. I needed to know how far we're going to get this. All right. Pmin. And there's one more, but I'll get Pmin posted first. All right, it's posted. All right, so here's the idea. You surveyed mosquito fish from 4 lakes around San Angelo. You recorded the number of Postidioplastoma minimum metacercaria. All right, you also measured water temperature and recorded the lake at the time of the temperature. We also measured length of those fish. All right, so it says lake, water temperature, and lake affect the number of parasites in the host. All right, so we're going to check the assumptions, find the simplest model, all right, and see what you get. where the VIF comes into play. How's it going?
Not very well. Why not? That's a good one. Yeah. You have anything committed?
There's maybe different models for the VIF, or maybe old model.
Did you simplify it first?
No,
So-
but
No, we skipped that step.
Oh, okay,
We just used Duncan to look at the tables.
okay.
That's big.
Yeah,
Much greater than 10.
a little bit.
In fact,
Just
possibly,
barely on the other side of that.
Yeah.
possibly 50 times.
All right. Get it?
Trying to help, man. Spells out correctly. Yeah, right, cool.
All right, so GBLMA, all assumptions accessible, or all assumptions are acceptable. So we look at our global stat. The link function, that's your linearity assumption. All right, that's what that linearity is doing. Do we have a linear relationship? All right, if we looked at a plot of our residuals, looks kind of funny because we've got the groups, but you know, for the most part, same thing applies. We're looking for scatter, you know, random scatter around this line. We don't want to see a pattern in any ways. We want normal QQ. If we violated non-normality, if we violated that linearity assumption, you'll see something that looks like humped here, or maybe, you know, like a valley. You'll see some sort of relationship, whereas this is just basically a straight line across. All right, so all of our assumptions are met, and when I work through this, I kind of get to this spot. All right, we have a significant interaction, right? And
Real quick, I can't get any of my code to run it off.
all right, what are you trying to do?
Well, I just tried to do GL multi.
Yeah, GL multi probably doesn't work.
Oh, okay.
How did you simplify it?
Yeah, it worked for me.
Yeah, mine wouldn't work.
And I can't even get my, I mean, it could be a simple thing, but I can't get my simplest model to save as its own vector either. Nothing will work, except for stuff I've already done, so I'm lost.
Did you simplify that enough? Did you update maybe?
I can't get super fun.
I think I tried it. Output, right? Output geomulti and weight table down, but I did that for whatever reason. It didn't work.
Yeah.
I restarted it already.
Go the long way around. I like this. I don't mind any of but I just don't like how key it is. You like it. It's pretty nice.
I know.
Very publishing. I'm thinking the future. That's how I'm going.
Yes, I couldn't get my GL multi to work, so you have to go back. Since all of our assumptions are met, up to this point, we have to utilize our ANOVA tables. I don't have temperature in here.
Right, so I mean, I know how to do that, so I just tried to skip it for time's sake, but now I just copied what the simplest model is out of the PowerPoint, and that won't save as its own vector or whatever.
Do you have that junk?
It's right here, yeah. Well, it's simplest model.
Yeah, because you don't have a lot that's counted, right?
Right, thank you.
Thank you.
Yeah, so your GL multi worked?
Yeah.
Here. What if, see, I'm gonna put mine up here.
You took them on full, I didn't try that one.
Which way?
I tried to type out.
Yeah, so I got mod full.
Okay,
Let's do output one. GL multi mod.full crypt equals. I get this. I get the same thing.
Mine's right.
Oh, I didn't run it on my notebook.
Right?
Oh, yeah.
Listen to this. Maybe it has an issue with pmin. It's capital. Make sure that works. Yep, that works. Now that works.
That is,
Ooh, hold on. Did I run across something like that? Pmin.
that is the dumbest reason why that doesn't work.
yeah, this is an equal.
Maybe it's this. pmin.int.
Okay.
Maybe that's what where it's getting into an issue. So capital P. Seems to work.
Yeah.
Let's look at this. I'll put that one. Type X. Yeah. So one point that I had was temperature, but we get this. All right. So this looks good. We've got a significant interaction. All right. So we're gonna have to be careful looking at lake and length. All right. What about VIF?
Do we need a subset actually here? We'll talk about it. I don't know.
What about VIF?
Okay.
Just VIF on my bad.
Okay. What did you get?
555.
I think we're on 3, but I got Lincoln went over it.
Oh, if you don't.
All right. Let's get this. Lake blank pmin. All right. I got my mod sip VIF mod sip. All right.
Square that.
So we get this. Yep. Got to square it, right? Yeah. Massive. All right. So what do we do here? Key is that we've got this interaction effect. All right. So that interaction effect really kind of defaults back to the main effects. So it almost looks like we have some sort of lake effect going on that's being correlated with our interaction. Are we surprised by that though? No. We expect that, right? So in this case, we see that these two are the ones. If we drop it, yeah, we're going to lose the correlation, but that's no big surprise. Right? That's no big surprise. So when we found these interaction terms, we can essentially ignore these VIFs at this point. Let's change this. Try something different. Whoops. I'm going to call it mod main only. All right, so VIF mod main. All right, so just do main effects. All right, I'm going to put all of them in there. And you can see that with the main effects only, we don't have a correlation. But if we're going to add one more variable to our model in the form of an interaction, now we're going to cause a significant increase in our variance inflation factor. So we're gonna do, I'm just gonna do these last ones. So now I just kind of take that main effect just to demonstrate how that interaction term is going to affect our variance inflation factor. Does that mean that we have a problem with collinearity? No. This is expected when we have interaction effects. All right? That's expected when we have our interaction effects. And that's kind of why we don't look at the full model, because our full model is going to have all these interaction effects built into it. And it'll lead you down the wrong path. Yeah. All right?
Why did you choose length and temp as the interaction effects?
I didn't. This is just demonstrating our interaction. This is just demonstrating how when we go from here, where everything is made, everything looks good. But if we had an interaction effect, look at how these things get jacked up.
Okay.
And it's because the interaction effect includes both length and temp. The interaction effect is in and of itself correlated to the main effects. So going back to our actual simplified model, where we have lake, length, and length interaction term, it's no big surprise that this is so high, because it's part of the interaction term. The interaction is, by its very nature, correlated with its own main effect. So we're good here.
Can you talk through that thought process again?
All right, interaction effect, right?
From where you did mod name, you lost me at mod name.
Yeah, I made these up. Simple. I made these up. There's no reason to do this. These are not simplified models. I made these up. The only reason we present these is to demonstrate. Stop. The only reason we do this, if we only have main effect, these three variables, the variance inflation factor are very low. They are uncorrelated. Right? If I then add an interaction, one more term, this isn't a new variable that we're adding. This is the interaction effect of two other variables. This term, by its nature, is correlated to these two terms because both of these go into it. So when we have a simplified model, a simplest model that has an interaction effect, we ignore the VIF of that. We expect this to be super high. We went from VIFs of like 1 and 2, all of a sudden we're up to like 300, 400, 500. And that's why when we found our simplest model and we do the VIF, it's so inflated. It's no shocker. It's no shocker, it's an interaction term. So at this point, we're good. All right? So key point, when you have that interaction term, you gotta be very cautious.
So do we even run a VIF after we have a significant interaction?
Yeah, because we're interested in that.
Oh, okay, so we just need one of the terms to be acceptable, or?
Oh yeah. This one, these are good. These are part of the interaction. Where was this other
If
one?
it was greater than 5, we wouldn't remove it.
No, we wouldn't remove it because it's still part of the interaction. Let's do this one. This is mod 3, I think, that I made. Here's a mod 3. So we have temperature now added to that simplified model, right? We still have a very high variance inflation factor here. Right? Because of the interaction, it's correlated with lake and it's going to be correlated with temp. But now we have length. This is why we would do a table. Length is by itself. If this one was greater than 5,
Then we would have a problem.
then we're going to have to start having problems.
Okay.
But this one, and these two are okay because they are part of the interactions. They form our interaction term. This is part of my simplification because I didn't have GL multi working. All right. Here's the hard part. Our interaction. All right, so we still have to analyze it as an interaction. And we've got two things to look at. We've got lake and we have the lengths. We can control for lake, right? We can take subsets of lake and we can analyze the relationship with the lengths. Controlling for length is another story. All right, so everything up to here, taking the subsets of lake, we've done that. Just take your subset and analyze this relationship. So, just as a demonstration, post hoc tests on the interaction. All right, so I have mod.sim. All right, so we're on mod.sim. So I'm going to say, I need to look at the levels. All right, so I'm going to make a subset. I'm going to make two subsets here. I won't do everything, but I'll make a subset of my pmin data set where lake is equal to buttes, and then make a subset where lake is equal to fisherman. And you would do it for Ivy and you would do it for Nazareth. All right, so I've got my subsets, and then mod views. We make our model. Count as a function of length. All right. And if we had another variable, if we had length, no, not length. What's our simplest model? Yeah, lake, length, temp. If we had temp, let's say temp was part of our simplest model, or we decided to include it, we have to include temp. It's part of our simplest model, but for us, it's not. We have length and lake. So we look at this model and we view our ANOVA table. All right, and it's significant. I'm sorry, it's not significant. So at Twin Buttes, our length and count relationship is not significant.
Why is
No,
that?
that's not right. Data dot buttes. That's better. There it is. Yes, we get a positive. We get a relationship. What kind of relationship? Well, you can look at a figure, or we do a summary, and we look at our coefficients. So with every 1 unit increase in our length, we're increasing the count by 2.8. So that's for Twin Buttes. And then we do the same thing for Fisher. So change this from mod Buttes to mod Fisher. Make sure we call this Fisher, Fisher, Fisher. ANOVA table. Significant effect. Now we have that type of relationship. So for 1 unit increase in length, we're having a 1.1 increase in count. And we would repeat this for the other links. Now, for like a real life analysis, we would probably stop there. We would probably stop there because we would recognize that that is kind of the relationship that we're interested in, we're focused on. But this isn't a normal class. All right? Because sometimes you'll have a reviewer that says, well, you can't just look at one, we have to look at the opposite. I want to know, do the lakes differ? All right, so the lakes present a harder type of analysis because of this length interaction. All right, so what we're going to have to do, or the way that you could approach it, is to take subsets of our length. Instead of taking, all of our entire range of fish here from, 35 up to 45 millimeters in length, say, I'm going to break it up and say, I'm going to take these that are less than 38 millimeters and analyze those fish. And then I'm going to take those that are between 38 and 40 and analyze those. So we're binning them to do our analysis. And our assumption is that since we're taking a much smaller range of fish, we've minimized the effect of that length variable on count. So you got a difference of, let's say, 36 millimeters up to 45 millimeters, and that could be 30, difference of 30 P minimum in there. But if we do a small, narrow range here, you're looking at a difference of maybe 10. Right? It's another way to kind of take a subset, but we're arbitrarily choosing these small enough sizes. So this is one way in which we can do it. All right. We say we're going to break up fish and say we're going to have fish that are less than or equal to 38 millimeters. We're going to have fish that are between 38 and 40 millimeters, those that are between 40 and 42, and those that are greater than 42. This is equivalent to taking our subsets. All right, and this is how we handle continuous variables. Now, how do we actually go about doing it? Same way, use our subset command to create individual subsets, or you can pass the subsets directly to the LM function too. So this is the script that I used to kind of step out that making my own data set. So we take subset, we do pmin, but now our selection length is saying we're less than or equal to 38. So less than sign equals says we're going to select out all of those rows where the length is less than or equal to 38. All right. For that next spin, we're going to go greater than 38 and less than 40. So we kind of did this with our subsets where we said we're going to select where lake equals Fisher, lake equals Buttes. We're just substituting our continuous variables and writing up these rational comparisons. All right, so when we look at all of these, we view our ANOVA tables, get our significance, and then run Tukey's. Why does Tukey's work? Because of our assumptions. So let's just kind of go through this again. What's that?
I said I'm gonna panic when we have to do this with our assumption violated.
As I said, in a real life situation, I probably wouldn't compare it. I would probably, we know the relationship, the graph, I think is sufficient to show that there's big differences between our lakes, and basically big differences, just across the board. But if you have a reviewer that says you only did it halfway, this is the only way to do it. This is the only way to do it. So we're going to do our bins. I already have the example where I pass it to subset. So we'll do DAT 38, DAT 40, DAT 42, and DAT 44. All right, so I'll make my individual data sets. So we're doing a subset of our P-min where length, all right, less than does not include the value 38. And what I did was just arbitrary. I said I'm going to include that upper number. So I did less than or equal to 38. Does it make a difference? No, just be consistent. All right. Just be consistent. So if you didn't include 38, then 38 needs to be included in the next group. So that's going to create our first subset. Our next subset is P-min. Now we have a length that's going to be greater than 38. So no, I didn't use the equal sign because we already included 38 in this subset. So it's got to be greater than 38, but it also has to be less than or equal to 40. So I want to make sure that that value is using the and, like less than or equal to 40. And again, it's just dividing up the bin. So that I'm capturing, I've broken it down into small enough sizes where that change in count hopefully is negligible from the smallest part of that bin to the largest size fish in that bin. And in that way, hopefully, we've neutralized the effective length. All right, so there's our subsets. And then we just go ahead and look at our models. So do LM, where we're looking at count as a function of lake. Data is dat.38, so this is the 38 size class, or 38 and lower. View the ANOVA table. It's significant. Lake is more than 2 levels. All of our assumptions are met. So run a two-piece table. Whoops. Of the AOB of our model. So you can see Ivy and Fisher are no different. And I bet if you run through this, you'll basically see that Ivy and Fisher are no different. Again, just kind of what the figure shows. All right. Word of warning on this, we need to pick a bin size that has a large enough sample size to permit our analysis, and at the same time has it where our smallest and largest values have minimal difference in our dependent variable. So this data set works great. This data set works great for that. But if we have different data sets where it really increases fast for a couple and doesn't really increase fast for others, we've got, again, we can have some issues. We can have some issues. And for that, if you run into that, come talk to me. We can talk about ways to try to address it. All right, so right up. I think the figure works, and I thought I had the code on here. Oops. Guess I don't have the code. No, don't have the code. All right, so I just kind of stepped through everything. Note the slopes. So this is where we kind of explain our relationship. We have significant terms, significant variables. Oftentimes it's good to mention what that slope is, either written out like this, or you can verbalize it, where the relationship is positive, where 1 unit increase in length results in an increase of 2.81, P minimum and so forth. I explained how I grouped by size. Again, if you have a reviewer, sometimes they're going to want it. Other times not. And if our assumptions are met and we get our subsets and we have significant terms, go ahead and use 2Ps. All right. Final one, flower visits. All right, flower visits posted. Go ahead and work on that. We will review our analysis on Wednesday. And what this one's different is that you'll notice now we are predicting we're predicting pollination visits. All right, and our independent variables now, we've upped it. We only have one categorical variable, that's flower color. All the rest are measurements. All right, does that change how we analyze our data? No, we still check our assumptions, proceed to find the simplest model. All right, and then once we get to the simplest model, then our next step for our post hoc test just kind of depends on what variables are included. All right, so kind of rewatch a video, look through presentation again. Do your best to go through flower visits, and then we will kind of go through it. We'll go through it.
What's correlation homework too?
Oh, I think it's a due date.
Not needed.
Do you guys do it?
Yeah.
I did.
Yeah, they have it on Wednesday, so if you have questions, we can answer.
Well, no.
I thought about that.
I did too until last night. I was like, actually, it's probably due today. But it's fine.
No, let's just make it due on Wednesday, so if you have questions, we could answer it. Hopefully the correlation was fairly easy.
Yeah.
Is that?
I think so.
Relatively.
It was a nice change of pace.
Usually
The write-up's not being a paragraph. Half page.
Yeah, that's very nice.
All right. Call it here. I guess I'll update the due date. Yeah, so our final exam is next week.
Yes.
And?
Yeah, so it will include, I mean, model simplification, but it goes back to like regular ANOVA to have a couple correlation questions on calculating means. Again, yeah, but I think my plan is to have it get posted on Friday.
Application.
Yeah, the take home part. Okay. That Wednesday is our assigned time. All right, so we'll make, we're gonna make it due by that.
Eight is, it's 6 to
Yeah.
8 is our.
Oh, yeah, we're gonna make it due like 6, so we can come in, if you have problems getting, we can fix it, to get it uploaded. The theoretical part, question and answer stuff, that'll probably go live on Tuesday, so then you have Tuesday and Wednesday to take it. But the plan is to have the take-home part posted on Friday, so you can kind of.
So are we gonna meet on Wednesday, or is it just like if you have?
No, if you have questions. We can continue lecturing on Wednesday. I don't plan on.
No.
Did we not have
I'll
lecture
learn all
on
this.
Monday?
No, because it's finals.
Okay.
No, we wrap this up. We're just gonna wrap up flower visits.
How
That's what
successful
we're gonna
is
wrap
this,
up. And I think this one has a variance inflation problem. I believe that's what we have.
Gotcha.
So I don't think there's an interaction effect. I don't think there's an interaction effect that'll be significant, and that allows us then to investigate some of those variance inflation factors.
Yeah.
All right.
That was gonna be my next question, like, is there gonna be a VIF with an interaction effect that's not made or taken?
Yeah, with an interaction.
Gotcha.
And that's why we kind of present it, because if you have the main effects, you have to pay attention to it.
Okay.
Sometimes you're restricted to the main effects just based on all your sample size.
So say there's a good interaction.
Yeah, you know, with Cameron. Yeah, she had hundreds of data points, but she also had like 30 some variables. You can't possibly have enough rows to do all your combinations, so you kind of had to start the main effects, in which case your VIS work.
Okay.
Because it's all about like the taking.
All right, what didn't work?
I don't want to about that. I don't mean to be that person. Yeah, I kind of felt like, okay, there's this, but yeah, so tomorrow, night is all of us just going through our presentation. Yeah, it's apparently 3 to 8 minutes.
No, it's B2.
I mean, technically, there's enough
So
time
length
for all of us to kind of talk for 8 minutes.
So what we did is we created a model. You got
There we go. So that'll be all the time.
summary.
Oh, and it is.
No, he's looks at all the analytics comparisons.
Yeah, it says it's calzone.
I literally have calzones for a birthday.
Right, however, if we had, let's say, length and temperature in there, we have to count it, we have to count it. Right. Yeah, and we look at the 8 over table to see do we need. This is really just looking at what's the relation between length. How does our intercept change?
Okay.
So when we take our subsets of length, then we're looking at the differences in the lengths. And then if the 8 over comes up, then we can do it too.
Okay, so I have one more question, 2 questions. When do you know the square?
In these things.
So if your degrees of freedom is greater than 1, just go ahead and square it.
Yeah, so if you have all continuous variables, your degrees of freedom will all be 1. So it won't even report this table. It'll just
Okay.
give you regular VIF numbers. But if you get a table like this where it has GVIF and the GVIF raised this, then you use your square and you use that.
Okay. So why did we VIF the simplest model to begin with? It looks like they're all significant.
They are, but we have to check it to see if any of these terms are correlated with each other.
And so we learned that late
So,
length.
yeah, for us, our simplest model was lake and length, where it included this interaction term, which means this term is also correlated with length and length, because these create this variable, basically. So this whole VIF is, we ignore it.
So what did we learn from doing this?
For us, nothing. I use this simply to say, when you have this interaction
Okay.
term, expect to see something like this. Don't panic,
So we should,
because you're gonna get it.
so should we have even, like, we got this, so I just don't understand.
Yeah, when
why
you
we
see,
did
when you
this.
get this, no, you don't have to do it.
Okay.
You don't have to do that step at all. Once you see the interaction, you don't have to do it. But if you have this lake and length interaction with lake and length, and then you have, let's say, extra main effects in there, then you better look at it, knowing that these 2 terms should be really high,
But you were looking
but
at.
we're
the
looking
other
at
hand.
all the other ones that are not part of the
Okay,
interaction term.
okay, that's starting to make a lot more sense. to me
So
now.
I think in this flower business, because we'll have, I think, 5 continuous independent variables, it hopefully kind of demonstrates the correlation between these variables.
Okay,
Hopefully.
thank you.
What do you got?
I was waiting on the wheel.
That's right, I have stuff for you, don't I?
Should motivate him to write.
Who? You?
Motivate me.